Welcome back once again, my dear brothers and sisters. It's very exciting coming your way all the time. My passion is, of course, to make you understand chemistry in the first place, to make you understand science in the second place, and to make you also understand the world in itself. And so when I come your way, I become very, very happy. Any up-and-coming person need a mentor. You need a teacher. You need somebody who can show you the way. Some people taught us, they showed us the way, and that is why we are here today and doing what we are able to do best. So follow us, follow LearnRite, and wherever you want to get to, of course, in your life, LearnRite is the guide that you need to get to where you want to be in the very near future. So today, we are going to continue with our lessons in chemistry. And before we continue with the current topic, I want us to just remind ourselves of what we did in the last video. Remember that in the last video, we discussed the three types of formulae that we have in chemistry: the empirical formula, the molecular formula, and then the structural formula. We said that the empirical formula was the formula that shows the simplest whole number ratio of all the atoms that are found in a compound or a molecule. The simplest whole number ratio. That may not necessarily be the actual whole number ratio. And so the actual whole number ratio of the atoms in the compound is said to be the molecular formula. And then we have the third one called the structural formula that actually shows how the atoms in the compound are bonded to each other in space. In short, we say structural formula is a spatial arrangement of the atoms in a given compound. So these are the three types of formulae that we discussed, and we worked examples on them. If you know the empirical formula and you know the empirical number or empirical unit represented usually by n, you are able to calculate your empirical formula. And knowing the formula, some experiment can also help you to determine the structure of that particular compound. We also talked about the percentage mass of any element or any atom in a given compound. We discussed that the percentage mass of any particular element or atom in a given compound. Usually, it is a fraction of the total mass of that compound times 100. Okay, whatever mass that atom has within the compound over the total mass of the compound times 100 gives you the percentage composition of that particular atom or element. We said all this. Just look at the last video and remind yourself of whatever we discussed. Today, we are going to talk about another important topic and a more concept called the chemical equation. Chemical equation. So here, remember that we are using the word equation. Equation means that you have the left side of a given system and then the right hand side of the same system. Now, in everyday life, we add something to another thing to get something. You add your gari and your sugar and you add water. Of course, you get your gari soakings. That goes into your stomach. We, in God's own mind, give us a number of elements. But in our wisdom too, the wisdom that God gave to us, we add certain substances together to give us certain substances that can give us some importance or use in life. Yes, God created something like sodium chloride already. It is salt. It is there. It is not the human being that adds sodium atom to a chlorine atom to get sodium chloride. God created the sodium chloride. But there are certain substances that God did not create. maybe A2SO4, which usually called sulfuric acid. In our own way, we see that sulfuric acid is important to us, so you have to create it by ourselves artificially. You can add some SO2 that is already created by God. You add water to it that is also already created by God, and you add maybe another oxygen to it that is also created by God, and then you come and get something like A2SO4, and that is very acidic, and A2SO4 is used widely in the world. So that creation is usually represented by an equation. I'm adding water, I'm adding SO3 or SO2, I'm adding oxygen, then I get H2SO4. So the things that we are adding to give you what you want all have names. The things that we are putting together are called the reactants. If I put A plus B and I'm getting another substance called AB, I call these ones the reactants, those that I'm putting together, and I call this the product. These are the reactants. And so in life, we continuously add certain things together to give us certain products that we think we need. Sometimes these products are also created accidentally. Someone is working on something, he's interested in something else, then you will see that, oh, another thing has been produced. Then you take that thing, test it, and see that, oh, that is also of importance. Then that also becomes another creation. But in short, what we are interested in regarding this chemical equation is that we can always add atoms or elements together to get compounds, or we can add compounds and compounds together to get other compounds. Or we can say we can add substances together to get new substances. And so in chemistry, we would bring it and say, we will use technical ways that you can add certain reactants together and get your product. And the product usually is that something that you want for a particular purpose. So all these are represented by a chemical equation. In mathematics, in chemistry, mathematics will use the equal sign. In chemistry, we will use this sign as our equal to, or forms, or produces. We come to the symbols that we use in chemistry. For now, let me demonstrate this reaction that occurs. You are adding a substance A to another substance B, and there's evidence that, of course, A and B has reacted to give you another substance. Let's see that by this demonstration. First, I have a number of substances here. In all of them, the reaction that I'm going to perform it such that you see something real, an observation, will be followed by what I do. And that will confirm that, yes, the substances that I put together, in other words, the reactant that I put together really did react with each other, or they interacted. First, I'm going to use these two substances. You see them, they have different colors. This is colorless and this is pink. In fact, this is labeled A and this is labeled B. I'm just using them to represent an acid. A is the acid and then B is my base. Okay, so I take my B base, I pour a little here. It does not change, it's still the B, that is the base. Now let me add my A to it, which is the acid. What do you see? The color is totally gone. The color is totally gone. And I'm seeing one uniform solution. What does that mean? It tells me that when I added the B to the A and the B reacted, they interacted, they mixed. So now in this solution here, in this beaker here, I don't have A, neither do I have B. I have AB, which is totally different from the A and the B. So these are my reactants, and that is the product. The observation by the naked eye to demonstrate that A and B has reacted is the color change. Because if you continue to put only B in the beaker, it will still look like B. And if you put A also in the beaker or anywhere, it will still remain the same thing. Unless something comes to add to it, Then if there is a reaction, you see a change. You see a change. Sometimes you can add a substance, say D, to another substance E. If they don't react, you see the two substances separating. They will still exist in the system, but they will not react. And that, again, you see by the naked eye that no reaction has taken place. But in this example, a real reaction has taken place. That is why the color change. Let me look at another one. Here you have to observe very well. I have a powder in this. This is labeled as calcium carbonate. Or someone will say any carbonate. I could have used sodium carbonate. I'm using calcium carbonate. I could have also used potassium carbonate. They are all salt. And this is calcium carbonate powder, solid. I have in this beaker here HCl. I have in this beaker here HCl. When I add this substance to it, just look at it critically. Please excuse me, let me empty this. So first, I'm putting in my carbonate before I add the HCl. Now watch it. What are you seeing? Some bubbles coming out. In chemistry, we call it effervescence. Some bubbles coming out seriously. Okay? In chemistry, we say the solution is giving out gases, and that process is called effervescence. Now, I'll explain on the board and write an equation to let you know why we're seeing those bubbles or that effervescence is taking place. Come with me to the blackboard. I'm going to write an equation for the first one. I did not write the equation. Let me go back and write the equation for the first one. The first one was an acid which was colorless plus a base which was pink. Whenever an acid reacts with a base, you are going to get what you call a salt and then water coming out. This has been determined to be true wherever an acid and a base, when you add them together, mineral acid, of course, let me qualify that. We have some acids that are not mineral acids. Some can be organic. Acid and a base, you get salt and then water. Specifically, let's see, what is it? Maybe HCl is an acid plus sodium hydroxide is a base. That is what I use. The colorless liquid there, which is labeled A, is HCl. The pink solution there is sodium hydroxide solution. When I add them, what do I get? I get sodium chloride plus water. So here I added this and that because they interacted to produce a new substance. Water is colorless, sodium chloride in solution in water is also colorless. So I had the overall solution becoming what? Colorless. So this and this interacted and we got this. In the second reaction, why did we see that effervescence? Whereas in the first one we did not see effervescence. In the second reaction, the substances that are added are calcium carbonate plus HCl. That is also an acid. Now when you add calcium carbonate to HCl, you are going to get calcium chloride. You're going to get calcium chloride plus water plus carbon dioxide. This is solid. This is aqueous. Now by adding this to this, I have my calcium combining with 2 atoms of chlorine to go and give me calcium chloride. It is salt, it's in the water. Then I have the carbonate here. The carbonate coming out as carbon dioxide gas, and then water, that is the 2 hydrogen here, also combine it with one oxygen atom to give me the water. Now, carbon dioxide is a gas. A gas in water. The gas will definitely want to come out. And so the gas paves its way and disperses into the atmosphere because it is a gas. And once it is a gas and it's coming out, that is why we had or we saw that sound or that observation. In chemistry, some effervescence. We call it effervescence. And normally, we usually just represented by the sound. So you may see in some books, people writing this. It's just a representation of the word effervescence and the sound. Okay? And in writing the chemical equation, because it's going to be evolved, we can put an arrow here. It is a gas. When you put an arrow here, it is telling that it is evolving to the atmosphere. That's a symbol. So that is why we saw that sound, effervescent sound. Now, there's another reaction that I want us to do, and then we'll look at another observation. Yeah, look at this. I'm still having my ACl solution. I'm going to add another substance to it. Let me do it in a beaker so we can see it. Sorry, in a test tube. So I hope you are seeing this solution. ACl solution. Very clear. Let me add this to it. As I've added this to it, I'm wondering if you can see. I can see some solid substances forming in it. Let me add more so the solid will come clear. You see, it has become something like starch. The solution has become something like starch. I added ACl, I put in ACl here, and I've added this substance. This substance contains silver ions. This substance contains silver ions. So it has become more turbid. That is very, very unclear. Looking like a starch solution. If it settles, you see the solid substances form there. Now, why is this so? This is so because of this reaction. I had my ACl. I'm adding a silver ion. Silver ion could simply be, say, silver nitrate solution. This is silver nitrate solution. This silver ion combines with the chloride ion here. So it gives me silver chloride plus HNO3. The hydrogen here combines with the nitrate, then the silver ion here, which is plus. In fact, there is a plus sign for the silver, a minus sign for this whole nitrate. So the silver combines with the chloride, and then the hydrogen goes to replace it to combine with it to give us nitric acid. Nitric acid is a solution that is in there. But this one, silver chloride, when you find it alone, it's a solid. It's called a precipitate. And so in that case, that one to represent this one, that sign, a precipitate, a solid that stays in there. A precipitate. That is the word, precipitate. And in simple terms, represent precipitate in chemistry as PPT, meaning that within the solution, you may find it forming something like a starch, okay, solid in the solution. And you can easily decant or you can sieve it. If you put a filter paper there, the pure solution will go down, okay, as filtrate, and can, of course, get the solid on top of the filter paper. As when I had filter paper, I would have separated the pure solution and the solid for you here to see. But try it in your laboratory, you see it. Add any ACl solution to a silver nitrate solution. you get a similar solution like this. And when you get it, just bring a filter paper and pour on it. The filtrate, which is a solution part, the HNA3 part, will go down, and then the silver chloride, which is a solid, will remain on top of the filter paper. Now, all these are illustrations or examples of reactions that occur. And so, all those substances on the left are called the reactants, and those substances on the right are called the products. Now, when I was doing this, I was writing, sometimes I was writing, you see that I have all these as the arrows. In chemistry, we have several symbols that we use. That is commonly understood by any chemist or any scientist. So the symbols that we use, I'm going to put them on the board. But before I do that, I want you to know that we have certain key characteristics of every equation, every chemical equation. And that chemical equation, the characteristics, you must know them. One, the equation must, I've written a number of equations here. One, the equation, the symbols of the compounds in the equation must be right. In other words, the substance HCl, that is hydrochloric acid, is written by this symbol or formula. Calcium chloride, what is calcium chloride? Yes, it's CaCl2. Because I've mentioned calcium and chloride, you cannot put CaCl1 there. If this 2 is not here, that is not calcium chloride. So this formula is the correct formula representation of calcium chloride. Water is rendered as H2O. So the first characteristics, the chemical equation or the compounds or substances in the chemical equation must be correctly represented by their symbols. Number 2, the state of the substance must be indicated. Whether it is a solid, as I've indicated here that this is a solid, whether it is aqueous, okay, the state of the substance must be represented. And this one, just as it here, water is liquid, calcium, carbon dioxide was a gas, represented by a gas. And then number 3, the number of moles, that is the relative moles, relative amounts, must also be indicated. Here you see that when I wrote 1 mole of calcium carbonate, I needed 2 moles of hydrochloric acid to react with it. If I put just 1 here, I will not get my equation to be right. And finally, the 4th one is that the equation must be balanced. Equation must be balanced. If you say equation is balanced, it simply tells you that all the total number of atoms on the left-hand side should be equal to the total number of atoms on the right-hand side. And of course, the number of atoms on the left, the types of atoms on the left-hand side will be the same type of atoms on the right-hand side. You can never write an equation or in any reaction, no new atom can be created. In short, what I mean is that when you have these substances here, you cannot go and have a new atom from these atoms there. No. I have calcium, I have carbon, I have oxygen, hydrogen, and chlorine. So there are 5 atoms on this side: calcium, carbon, oxygen, hydrogen, and chlorine. They should be the same atoms here. That's why I have calcium, chlorine, hydrogen, oxygen, and carbon. You cannot create any new atoms. In other words, from this reaction, I could not come and get a nitrogen compound here. It won't happen. Okay, it will not happen. So that is what we mean by a chemical equation. So, what will you say a chemical equation is? What will you say a chemical equation is? Think about it. A chemical equation, of course, can be said to be an expression in symbols of the relative amount of substances taking part in a reaction. An expression. This is an expression. The whole thing is an expression. An expression, but in what form? They are in symbols. Calcium representing C representing calcium, carbon representing carbon here, oxygen representing O representing oxygen. When you write all of them together, this whole thing is called calcium carbonate. So an expression in symbols, okay, of the relative amounts, a number of moles of substances that take part in any reaction. A chemical reaction is an expression in symbols of the relative amounts of substances taking part in a reaction. That is the definition of a chemical equation. And when we say what is a balance equation? A balance equation, of course, is one in which the total number of atoms on the left hand side equals those the same number of atoms on the right hand side. That is a balanced equation. Very soon, or in our next video, we are going to be looking at how to balance equations. If you are not able to balance equations, of course, you cannot answer any question on chemical equations. Before I wrap up on this, let's see some symbols that we use in chemical equations and their meaning. We have for the states of the substances, we have S representing solid. S means solid. L in brackets means liquid. And then we have G in brackets meaning gas. Then we have aqueous meaning aqueous. Aqueous, remember, I've mentioned before in one of your videos. We said a solution where the solvent is specifically water is called an aqueous solution. But where you have a solid dissolved in a solvent and the solvent is not water, then you can call it ordinary as a solution. Okay? If I pick any substance and I use petrol and dissolve that substance in the petrol and it dissolves, you cannot tell me, you cannot call that solution an aqueous solution. You can just say solution, or someone will say a petrol solution. But specifically, when the solvent of any solid solvent mixture is water, we call it an aqueous solution. Representation is aqueous. I also introduce some other formula for you. This sign means that to evaporate, effervesce, for gases, it leaves the system, okay? And then we have this, also meaning a solid form, that is a precipitate. Solid form. So this usually we say precipitate. And this is a gas, evolution of a gas going out, okay? And we have other symbols. This one, that is what we use most. We say it goes to form. Forms the product. We have this. It means that it forms in both directions. The reactants here, for instance, can go to form this. At the same time, this product here can also probably react to come and form this. So if you see this, we say it forms in both directions. But be careful. We have this, and that is different from another one, which is this. Okay? Which is this? This one, look at it, the arrows are not full. They are different from this. And this reaction here, assuming I did this, assuming I wrote this one like this. What this one means is that it is forming in this direction. At the same time, these products can also act as reactants and react to come and give us the initial reactants. It is the same as this, but when the reaction starts, when you have such a situation, we call that reaction a reversible reaction. It means that the reaction can go to the forward direction from left to right. At the same time, the product, if is not managed, is not controlled, can also react to come and give you the reactants. Such a reaction is called a reversible reaction. And in any reversible reaction, initially, you can use this. You can use this symbol. It forms in both directions and then that. But there comes a time, there's a particular time in the process of this reaction where the rate at which the forward reaction goes to form the products and the rate at which the backward reaction, that is the rate at which the products also react to come and form back the reactants, become the same. When they become the same, at that point, you cannot use this symbol, but the symbol you use is this, meaning that we have reached what we call an equilibrium. We have reached an equilibrium. So when you have that equilibrium reached, then you can represent that reaction by this and say that reaction is particularly at an equilibrium reaction. This symbol shows that it can form in this direction and form in that direction. But sometimes the rate at which the forward reaction will go is far more than the rate at which the backward reaction will do at will occur. So if we have such a reaction, then you are comfortable to use this reaction. But as long as that point is reached where the forward reaction, the rate of the forward reaction is equal to the rate of the backward reaction, then we say the equation is an equilibrium, and that is the symbol that we use. So most often, for all reversible reaction, is found mostly that a time comes that you have a reversible, you have equilibrium reaction. So you hardly see this symbol. You hardly see this symbol being used in most of your books. It is this one that you find, telling you that if that reaction starts at a point, equilibrium is reached. The rate at which this is formed, and that the product also react to form the product, becomes equal. At that point, we say the reaction is at equilibrium. That is a major topic that we treat. Okay, we call it equilibrium reactions. A very interesting topic. We'll look at that. And the symbol we'll be using over there is this. In some old books, we also have this sign, an equal to sign, which you hardly find now. It's called a stoichiometric. Remember, we have done this. Stoichiometric equation, okay? That is also, again, no more in use. But there are symbols that those of you who become professors will be reading old books and all that, you find them, okay? But currently, what we'll be interested in, we'll be very much interested in, are these symbols: solid, liquid, gas, aqueous state, a gas evolving, or a precipitate being formed, and then this bigger symbol. Most of the reactions, you see this, says that it forms in that. And then you also see this. So this may also not be seen in most of our equations. I hope I've explained everything clearly. And so, now that you know how to write, now that you know what a chemical equation is, an expression of symbols of the relative amounts of substances taking part in a reaction, and know what a reaction is. Of course, most reactions are followed by observations. You see that the reactants that you put together have really reacted. We are going to go ahead to look at how, when your substances are mentioned, how you put the A and B, that is the reactants, together to give you the product, and how you'll be able to balance the equation. Any equation written which is not balanced is no equation, my brother or sister. So our next video, we are going to look at balancing of chemical equations. Balancing of chemical equations. And when equation is balanced, that is when you know the relative amount, the mole ratio. And that is the ratio that we use in doing all calculations in chemistry. All calculations in chemistry involving one substance and another, you need the mole ratio. So if you are unable to balance your equation, or if you are unable to write the correct symbols and correct equation for a given reaction, my brother or sister, you cannot attempt that question. In our next video, come with me. We are going to balance equation. Though difficult, but you will learn right. Don't be afraid. We'll make big things very, very small. Me, I'm a villager. I remember one musician called Papa Yankson of blessed memory. He said, if you have made yourself a very big tree, me, I have made myself a very small axe, and I use that small axe to cut you down. LearnRite, we cut very big problems down with our small techniques. Come along in balance of equations in the next video. Thank you.